All right. Okay, so let's get going on today's class. So what we're going to be doing today is we're going to be going over the kind of last little bits that you need to do this first basic type of hypothesis test. So we'll finally fill in the last of the blanks so that you can do 4 out of the 5 steps, with step 3 coming in on chapter 6. But before we get to that, just a reminder that we do have exam number 2 coming up in just over a week's time. So it's going to be on Thursday, October 18th. It's going to cover chapters 4 and 5. So it's going to cover the unit normal distribution table, unit normal distribution curve, and probabilities. It's going to cover starting with a raw score and getting a percent, starting with a percent, getting a raw score, and also hypothesis tests from chapter 5. So just those 2 chapters, and it's going to be a computational exam, just like exam number 1. It's going to be in Excel. That'll be available through Canvas. You have to be here when you're completing it. There'll be 8 questions, and once more, it will be open book. By which we mean open any resources that you want to use except other people. So no communicating, no Skyping, no FaceTime, anything like that. However, anything else you want to bring is fair game. So lecture notes, these Excel sheets that we're going to go over today, any notes that you want to make yourself, those 2 pages, those 2 slides that help you make the decision on step 5 as to whether you accept or reject a null hypothesis, whatever you need. You can bring to your to the exam. It is open any resources that you might want to use. So we are going to have our review session next class. That's Thursday, October 11th. It's a little bit early because we have the fall break coming, but this is the class before the exam. And as always, it's going to be an open review session. What that means is it'll be student driven. So bring your questions, let me know what you want to see. I won't have anything particular that I'm thinking of covering that day. So basically come here with your questions and we'll go over and make sure that everybody kind of gets a tailored experience so that they can prepare best for exam number 2. But because of that, it's optional as well. So if you want to extend your fall break a little bit longer, feel free. But whatever you think is the best way for you to prepare for exam number 2, feel free to do that. So if it's something other than the review session, no worries. Otherwise, come on down to the review session. I'll be here and we'll be ready to go. All right, so back to hypothesis testing. Back to going intelligently and systematically from knowledge about a sample to conclusions about an entire population. So this, again, is where all of the practice that we've been going through comes into play. So all of the practice we've been doing on calculating means, calculating standard deviations, calculating those z-scores, unit normal distribution tables, all of that practice is going to come together right now in the hypothesis test. And this is where we can finally do that kind of cool stuff, answer those questions that we have about psychology, about behavior, but again, do it in an intelligent way that allows us to remove any sort of human bias from our interpretations. Now, as I said before, we're not dealing with the full-fledged, more complicated hypothesis tests. We will, as we move along, we've kind of introduced a simpler version. But at this point, we've been looking at this 5-step procedure. And so far, we've covered a number of the steps. So at this point, we've looked at all 5 steps. So you can think of it as 5 steps in terms of your training. And what we want to do is get to the point where you can do all 5 steps and you will be ready to do your hypothesis tests alone. So without any additional input from me, just data, question, and you'll be able to do your hypothesis test. And we're getting there, but we're not quite there yet. So we do have step 4. We've done step 4, the calculation of your samples score on the comparison distribution. We got step 5. which is making the decision whether you accept or reject the null hypothesis. Today, we're going to complete step one. We kind of know how to do part of step one right now, so today we'll go through the full-fledged step one. Step two, that comparison distribution, and step two, the comparison distribution, step three, your cutoff scores. We'll get to those later on, but for right now, let's tackle that step number one and that step number three, so that you only need to be given the comparison distribution, and again, that's coming up in chapter 6. So kind of let's finish this, the pieces of the puzzle, the pieces of the training that you've been missing, and that's what we're going to be doing today. To take care of step number one, we're going to take a look at one-tailed and two-tailed hypothesis tests, and that will also allow us to do step number 3. And then we're going to have some time for hypothesis testing process in class demos. We're going to go over self-esteem, the self-esteem physical education experiment one more time, and this time we'll do it completely the right way. And then you can practice on some psychology studies, classic psychology studies that have to do with memories for car crashes and the effectiveness of timeout penalties on adults and changing their behavior. All right, so the hypothesis testing process, still working with the 5 steps. So step number one, restate the question as a research hypothesis and a null hypothesis about the population. Step number 2, determine the characteristics of the comparison distribution. Step number 3, determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. Step number 4, determine your sample score on the comparison distribution. And finally, step number 5, decide whether or not to reject the null hypothesis. So the last little piece that we need to get steps 1 and 3 to the point where you can do them on your own is the difference between a one-tailed and a two-tailed hypothesis test. And again, this is what we need for a full understanding of step 1 and step 3. All right, so what's the difference between a one-tailed and a two-tailed hypothesis test? Basically, it's how you're asking your question, what is your question asking, in other words, and the impact on where you draw your lines in the sand for your hypothesis test. So far, we've only been doing two-tailed hypothesis tests. And a two-tailed hypothesis test is so called because the comparison distribution, you draw lines in the sand so that it has two tails. It has a lower tail and it's got an upper tail. Two tails in your comparison distribution, 2 lines in the sand, that's a two-tailed hypothesis test. On the other hand, sometimes because of the nature of the question you're asking, you want to do what's known as a one-tailed hypothesis test. A one-tailed hypothesis test, like it says on the tin, only has one tail, only has one line in the sand, only has that one critical area that you're looking at. So the two-tailed hypothesis test or the one-tailed hypothesis test, which one you use, completely depends upon what's the question that you're asking. So some questions are what's known as non-directional hypotheses. And non-directional hypotheses is when you're testing whether your treatment has an effect, but you have no idea which way your treatment might go. So this is when you're just asking, does the treatment have an effect? Maybe it's going to increase scores. Maybe it's going to decrease scores. We don't know, but we just want to see, does it change scores? Does it have any sort of an effect? That's a two-tailed hypothesis test. That's a non-directional hypothesis. On the other hand, for a one-tailed hypothesis test, this is where you're looking at a directional hypothesis. This is where you have a specific direction, and that's the only direction you're interested in. That's the only direction you want to test. So in this case, rather than saying maybe the treatment has an effect, maybe the treatment changes scores, maybe it goes up, maybe it goes down, that's a non-directional hypothesis. On the other hand, if you want to know, does the treatment cause an increase? And that's all you're interested in. Does the treatment cause an increase? Then you do a one-tailed hypothesis test. So for example, if you we're looking at the effects of social media on depression. Social media on depression, some theories say the higher use of social media will increase depression because you're constantly comparing your average to everybody else's best. Other theories say social media would actually lead to a decrease in depression because social media allows you to connect to other like-minded people so you don't feel as isolated. So will it cause an increase in depression? Will it cause a decrease in depression? We don't know. So in that case, you would want to do a two-tailed hypothesis test. If, on the other hand, you're looking at a treatment for depression, well, let's not do depression. You're looking for a treatment for math ability, right? You have this new program that you're using in your classroom, and you think that this new math program is going to change math ability. You're not interested in whether or not this new math program is going to decrease math scores. You're not interested in whether it's worse. You're only interested in whether it's better. So will this math program cause an increase in math scores? That's a one-tailed directional hypothesis test. And on the flip side, back to depression, if you develop a treatment for depression, you're not interested in whether or not your treatment causes an increase in depression. You're not interested in whether your treatment makes depression worse. You're only interested in whether it decreases depression. So in that case, you take the entire tail and you pop it over onto the decrease side. And you draw your line in the sand on that side because you're only interested in, does the treatment cause a decrease? Yep.
Is this where biases come into play? People only look for the answer that they want?
This is not necessarily where biases would come into play, but this is something that you have to be very careful with when you're using a one-tailed test, and some scientists don't like to use one-tailed tests because of this. You have to make your decision on the direction before you see your data. Because the way that it's going, or what you're doing, is you're taking all this uncertainty, and in a two-tailed hypothesis test, you're splitting it up between the two tails, because you don't know which way the results might go. You don't know if it'll increase, you don't know if it'll decrease. So that's a fair way to split up that uncertainty. On the other hand, if you think it's going to cause a decrease, that's a fair way to split up that uncertainty. What you can't do is you can't say, all right, I'm going to do a two-tailed test. So let me draw my comparison distribution here. And I got my cutoff score over here. And I got my cutoff score over here. And then you notice that it's an increase. Then you notice that your mean ends up over there. At this point, it's unethical, it's incorrect, you can't do it. You can't change your mind and say, oh, well, let me just take this and I'll stick it all in one tail, and lo and behold, I have a successful experiment where I have a significant finding. That you can't do because this increases your alpha rate. All right, and as we're going to see, what you do, that alpha rate, that probability that you'll that you'll conclude that something is there when something actually isn't there, that gets split up into your two tails or put all into one tail. And that's the only way that you can do this, and you have to do it before you take a look at your data. All right, so if you have no reason or no particular interest in only one direction of an experiment, and you do a two-tailed hypothesis test, that's going to influence where you draw your lines in the sand, right? That's going to influence step 3 when you take a look at your cutoff scores. On the other hand, if you do it a one-tailed test, you're going to have a different cutoff score. So now's where we're going to find out how we actually find those cutoff scores. Now we're going to see how we actually get those numbers, those lines in the sand, those z-scores that tell us where these tails are. And the way that we get them, you might have guessed this already, is we go to that unit normal distribution table. And the unit normal distribution table depending upon the percentage in the tail, is going to tell us the z-score that's associated with those cutoff scores. So let's say that we are doing a one-tail test. So let's say that we're doing a one-tail test over here, and we have an alpha of 0.05. As I mentioned, alpha is the size of your tails. So if we have an alpha of 0.05, and we're doing a one-tail test, so we'll stay with the decreased one-tail, that means that we put all of our alpha, all of that probability, we put it all into one tail. So if our alpha equals 0.05, that means that it's 5%. And if it's a one-tail test, that means that all 5% are in that one tail. So if you remember chapter 4, in our work with the unit normal distribution table, we got 5% in a tail. We have to go to our unit normal distribution table, look at the percentage in the tail, scan down until we find 5% in the tail. 4.95 or 4.05, those are both equidistant. In your homework, I believe it's 5.05. If it doesn't work, try 4.95. In the exam, either or will be acceptable because 5.0 is right smack dab in the middle. Let's go with 5.05. We find 5%, or as close as we can, in the tail. We scan across. There's your z-score. It's on the negative side. That's your cutoff z. Minus 1.64 is your line in the sand. Minus 1.64 is your cutoff z-score. That defines where your tail is in your comparison distribution. On the other hand, if it's a two-tail test, if you have the same alpha, let me see if I can get a more vibrant marker here. So you got the same alpha, you still got a 5% alpha. However, now, it's not better. Okay. Maybe, yeah, let's go with that. All right, so now we're doing a two-tail test. We're doing a non-directional test. We still have an alpha of 0.05. That still equals 5% in the tails. But now we got two tails. So we got the tail on the lower end. We got the tail on the higher end. Both of those have to be the same size. 5% divided by 2 means that we got 2.5% there. And we got 2.5% there. We got to find what our cutoff scores are. So we got percentages. We need z-scores. We go back to our table. We scan down for percentage in the tail. This time, very nicely, we got exactly 2.5% in the tail. We see the associated z-score, 1.96. So our cutoff scores, and this is where we've seen the 1.96 before, positive 1.96, negative 1.96, and we have our cutoff scores for that particular alpha. So that's the reason why you need to know whether you're doing a two-tailed or a one-tailed, because the same percentage for a one-tailed goes all in one side, all on one tail. That percentage in a two-tailed gets split up against the two tails. And that's why you can't change your mind afterwards. Because if you said, oh, my mean is over here, can't I just do a one-tailed now? Well, if you do, and you switch over to this situation over here, you still carry over that 2.5% that you had before over here. And instead of having an alpha of 0.05, you've inflated it to 0.075. And that's just not allowed. You just can't do that. So that's why you have to make that determination before. Are you doing one-tailed or are you doing the two-tailed tests? All right, so that was for an alpha of 0.05. Occasionally you'll see alphas of 1% as well. So same situation for 1%. If it's a one-tailed test, and you have a 0.01 alpha, we have 1%. That whole percent goes into the one tail. We go back to our unit normal distribution table. We search for 1% in the tail. 0.99 is the closest one on the table. Z-score associated with that, 2.33. So again, if it's on the decrease side, we got minus 2.33. If on the other hand, it was an increase question, a greater than question, does the scores go up? It would be positive 2.33. And then if we're doing a two-tailed test with an alpha of 0.01 or 1%, we still got to split it up. So we put 0.5% on the positive side. We put 0.5% on the negative side. We go to our unit normal distribution table. We look up 0.5% in the tails. Once again, not that friendly. So we'll go with the closest one, 0.51. Look up the associated z-score, 2.57. And our cutoff scores, in this case, is 2.57. So minus 2.57 and positive 2.57. All right, so that is how you do step 3, finding the cutoff sample score on the comparison distribution. You determine whether it's a one-tailed or a two-tailed. You determine your alpha. If it's one-tailed, your entire alpha goes into one tail. If it's two-tailed, you split your alpha amongst the two tails, and then you go to your unit normal distribution table and look up those z-scores that are associated with that percentage in the tail. All right, any questions on step 3? All right, last thing we need to do is step 1. So step 1, restating the question as a research hypothesis and a null hypothesis about the population. We've done that two-tailed so far. So what we've seen so far has been two-tailed hypothesis tests where we have a research hypothesis and a null hypothesis. Now, one thing that's going to help you out making these two hypotheses for your one-tailed and your two-tailed tests is that your hypotheses, your null hypothesis and your research hypothesis, has to cover every single possibility that can be an outcome of an experiment. So what are the possibilities of your experiment? Well, one possibility is that the mean of your treated population is going to be less than the mean of your untreated population, right? Maybe your treatment makes scores go down. That's one possibility. Another possibility is that the mean of your treated population is going to be greater than the mean of your untreated population, right? Maybe your treatment makes scores go up. That's another possibility. So we got one possibility, your treatment makes scores go down. We got another possibility, your treatment makes scores go up. There's one last possibility, your treatment does nothing, and the scores stay exactly where they are. Those are the only 3 things that can happen. And your research hypothesis has to cover all of those possibilities. Sorry, your 2 hypotheses have to cover all of those possibilities. So what happens in a two-tailed test? Well, in a two-tailed test, we have the research hypothesis that says that the treatment does have an effect. So this, and the null hypothesis is that the treatment has no effect. So the treatment has an effect is written as your treated population does not equal your untreated population. The mean of your treated population does not equal your untreated population. And that covers the fact that your treated population might have a lower mean, and it also covers the fact that your treated population might have a higher mean, right? It's just saying it's not equal. So it's either less than or greater than. That's the only way you can be not equal. Your null hypothesis, the treatment has no effect. Very straightforward. The mean of your treated population is the same as your untreated population. There's your null hypothesis. Two-tailed hypotheses covers every possibility. Research hypothesis covers greater than and less than. Null hypothesis covers equals to. So that's the two-tailed hypotheses. Those are the ones we've been doing so far. Any question on the two-tailed? So far, so good? All right. What about the one-tailed? So let's say that the research hypothesis is that the treatment causes an increase. So this is going to be one-tailed increase. All right, treatment causes an increase. That's your research hypothesis. Again, notice one-tailed, directional. Treatment is going in one direction. Treatment causes an increase. The null hypothesis is always a complete opposite of the research hypothesis. So if the research hypothesis is that the treatment causes an increase, your null hypothesis is that the treatment does not cause an increase. Right? That's a complete opposite of the treatment causes an increase. Treatment causes an increase, we write that out as the mean of your treated population is greater than the mean of your untreated population. So now for the one-tailed, the increased one, that possibility that your treatment increases scores is covered by the research hypothesis. Your null hypothesis has to cover